Okay, let's see what we remember here. So our initial situation is this. Okay, the general E jumps, okay, off of that ramp. The ramp is angled 20 degrees above the horizontal, and it launches at 32 meters per second, 20 degrees above the horizontal. And it follows a perfect projectile arc down to the ground on the other side. Okay, assuming the launch point and the landing point are level, okay, they're the same height, okay, we would have a situation that looks like this. Now, we have to break up all projectile motion into its horizontal and vertical components because they act differently. Okay? All we're given is the launch velocity, magnitude and direction. And we're being asked to calculate two things: horizontal distance traveled and maximum height. In order to calculate those two things, we're going to have to calculate a couple other things too. Okay? 3 other things in order to get there. Right? One of those things, okay, and I'm going to make the vertical stuff red here, is the initial vertical velocity, or the vertical component at time 0 of the general E's projected speed, or projected velocity. Okay? That's going to mean the y component of its projected velocity. So if I'm going to get the initial vertical velocity, that's going to be the sine of 20, because it's the opposite side, times 32. I think we got this far on Friday. Okay? So we got sine of 20 times 32, right? So 10.94 meters per second, and I'm going to make that positive because it's up, right? One of the other things I know vertically is the acceleration, and it's negative 9.81 meters per second squared. In a question like this, where the object is projected at an angle, I have to make gravity negative because I'm going to have a change in direction. Initially, the generally is moving up, but at the end it's moving down. Everyone follow me there? Okay. Now here's the thing we have to remember. If the initial height and the final height are the same, okay, then how do the initial velocity and final velocity vertically compare? Yeah, they're the inverse of each other. Okay, so when I throw this marker up in the air, this is what the general E does from just a vertical perspective. It leaves my hand and it immediately begins to slow down. Okay, so let's say it leaves my hand at 10.94 meters per second. It slows down, it slows down, it slows down, it comes to a stop, okay, and then begins to actually fall back, right? So it accelerates at the same rate over the same distance. It had better come back to my hand at the same speed it left at. Agreed? Because everything else is equal, right? So that means that in this situation at least, VF will be negative 10.94 meters per second. Right? If those heights aren't the same, then that's not true, and I would have to go about this a different way. It doesn't make it any harder, it just means I have to go about it a different way. All right, so now I've got that information. Okay? From a horizontal perspective, the horizontal component of the projected velocity, okay, is going to be that constant horizontal velocity that the car travels at. Okay, so we'll call that V horizontal, and it's going to be the cos of 20 times 32. All right, so 30.07 meters per second. Okay, so I'm trying to find, let's find this first, the horizontal displacement of the general E. What do I need? Time, okay? Because horizontally it travels at a constant velocity, and I know that horizontally speaking, this is the formula I have to use. Okay? I don't have time. Can I find time with the information I was given vertically? Yeah. Yes. All right, and I think that was actually where we got to on Friday, was actually getting the time. Okay, so time will be VF minus VI over A. So that'll be negative 10.94 minus 10.94, negative 10.94 times 2, okay, divided by negative 9.81. All right, so I'm going to shortcut and take that number there, All right, so the general Lee is in the air for 2.2 seconds. All right, so that I can bring over to this side. Are they all right with that? All right. So now I can go V equals V times T, take my 30.07, multiply it by 2.2, and I believe it comes out to 67 meters horizontal. Okay. Everybody all right with that? Now, the second thing that we're asked to calculate is the maximum height, or the vertical displacement maximum of the general Lee. Okay? That occurs halfway through the flight. At that instant where it stopped for a second vertically, it's always moving because it's moving horizontally, but from a vertical perspective, that's where it stops, okay? And then falls back down. So, since it's stopped at this point for an instant, what do I put for its final speed? 0. Okay, so I know that right here, VF is 0 meters per second. Okay, and I'm looking for the vertical displacement. So I know VI, that didn't change. I know A, I know VF, and I'm looking for D. Do I have a formula that has those things in it? Which one? D?
D equals V over T.
Nope, I can't use V equals D over T for an accelerating object.
Could you use time, or could you use one of the ones that have like time squared, or would you use velocity final because velocity initial plus 2?
That's the one I would use. Okay, I would use this one. VF squared equals VI squared, I've got those two numbers, plus 2A, which I also have, times D, which I'm looking for. Right, so I manipulate that for D and say VF squared minus VI squared over 2A will give me the maximum height of the general Lee. So that'll be 0 squared minus 10.94 squared divided by 2 times negative 9.81. Right, so I'm going to take that and square it. Okay, and I'm going to divide that by 19.62, which is 2 times 9.81. Okay, so the maximum height of the general Lee is 6.1 meters. This is why these cars don't survive the jump. That's the equivalent of dropping a car off the top of the gym. Car not like that. Okay? It's gonna break. Something's certainly gonna break. Okay? And that doesn't even include the fact that it's also moving horizontally at the same time. Okay? That adds a whole other kettle of fish to that. Okay, so our maximum height there will be 6.1 meters. Now, is there another way I could have done that? Brooke mentioned I had time. Could I use something with time?
Isn't it like, I forget what it is, but it's like D equals VF time, subtract 1/2 AT squared.
Yeah, I would suggest that we could use this one. We could do that. We could also use this one.
Or VI.
Right? VI is not 0, okay? And we can do this because we have time. Here's why I caution you against using these two formulas to do this. It's totally legit to do it that way. But what do you have to remember?
V is 0.
Well, and if you're using VF, VF is 0, yes, but there's something else you need to remember. When in the flight does this occur?
Horizontal, halfway through.
Halfway through. How much of your time do you use? Half. That's what people forget. Okay? They do this and they plug in the full time. Well, that doesn't work. Okay? In fact, if I use the full time, what should this come out to? Right, my final vertical displacement, which in theory for this question should be right. Okay, so that's why I caution you not to use this. You can, but you have to remember to half your time when you use it, and most people don't. Okay, so that's why I always use this one. It doesn't even involve the time. Okay, it's all numbers I was given in the question, well, except for VI, which I calculated, but okay, I don't have to worry about forgetting to half the time when I plug it in. Okay, it's just, I find it's more reliable for people, but it is perfectly legitimate to do it the other way. Just remember to half your time. All right? Okay.
So,
Oh,
sorry,
yeah.
so when you half your time, you would go half of 2.23,
Yes.
and then you'd just do one, at the end it's like t squared, so would you half that, like just do one?
Yes, so I would, like if we do this, let's actually plug it in and I'll show you that it comes out to the same thing. So this will be 10.94, so I'm using this formula here, times that 2.23, okay? Plus 1/2 times negative 9.81 times 2.23 squared. Okay, so if I plug that in, so I take that initial speed, that one, times the time I calculated, that, plus 0.5 times negative 9.81 times that number squared. Whoop, I messed something up.
You didn't have your time.
See? I didn't half my time. What did he tell you? I didn't even do that on purpose. I was just, that's why I don't do it that way. I always forget. Okay, and what did I get? Practically 0. Practically, right? Times 10 to the minus 9, which is much, okay, so like the ground on that side was a little bit lower. Okay. So it does, that's why I caution you against doing it. But if we did it right, so I took that number and divided it by 2. And then try this all over again. I will get the right answer. There. It's exactly the same, right? There's the way I did it the first time, using that formula. There's the way I did it using the right time this time. Okay? I get exactly the same number. It's perfectly fine to do it that way, but don't be like me and always forget to half your time. All right, is that making some sense? That's a very typical, like I would totally put that on a unit exam type of question. Hint, hint, I'm totally putting a question like that on a unit exam. Yes. Okay, so this one's just like that. Try it on your own. Okay, without me walking through it. Then I have another video show you. Okay, so this one sets up just like the last one, but obviously they don't all always ask for the same things. Okay, and we're going to go through some examples today of questions that work a lot differently. I mean, the fundamentals are still the same. I still need, VI, vertical, and V horizontal, stuff like that, but they ask you for slightly different things, or they give you different things. Okay, and we're going to look at some of those. So for this one, okay, we start off with the cannonball being fired. That's not really a 40-degree angle, but we'll pretend it is. Okay, at a speed of 140 meters per second. Okay, so that's going to go like this, follow a projectile arc, just like everything else does. All right, so vertically speaking and horizontally speaking. All right, this initial or projected triangle is always the same. This side is always going to be VI vertical. Okay, and this side here is always going to be our constant horizontal velocity. Okay, because they are the components of the projected or fired or launched velocity. So V horizontal then, okay, for this question will be the cos of 40 times 140. Right, so 107.25 meters per second. Okay, and then we'll have our initial vertical velocity, which will be the sine of 40 times 140. Okay, so 89.99 meters per second, and that's going to be positive. Since they don't tell me otherwise, can I assume that the landing point is level with the launch point?
Yes.
Yes. So that means VF is going to be negative 8.99, or 89.9, sorry. Now, if it wasn't different, or sorry, if it was different, if the vertical displacement wasn't 0, I would then know what the vertical displacement was. Agreed? Okay, would I be able to use that as one of my givens in the vertical part? Okay, and then I would still be able to do this. It would actually be more like your horizontal questions that we did where you drive off a cliff, except this time you're being like projected up. Okay, you still have a vertical displacement, so rather than having VF, instead you have D.
Say it was like, say a cannonball was fired like on top of a mountain downwards, wouldn't you still have a vertical displacement from the edge of the edge of the mountain to where it was fired? Like?
You would, but that's not where it ends.
Yeah, no, where it ends.
Oh, yeah.
Down there.
Yes, you would. So VF and VI wouldn't be equal.
Mhm.
You wouldn't know what VF is,
Okay.
but you would know what D was.
Yeah.
And the question would have to give you probably one other piece of information, like it might have to ask you or give you time or something like that. Yeah. All right, so, or you could calculate it because you would know D. All right, and then A is negative 9.81 meters per second squared. All right, so I'm looking for the maximum height and I'm looking for the horizontal displacement. So just like we did with the last one, we can calculate time with our vertical information. So we'll say that time equals VF minus VI over A, so that'll be negative 89.99 minus 89.99 divided by negative 9.81. All right, so in the air for 18.35 seconds. All right, so that I can bring over here, 18.35 seconds. Now I can calculate what D is. Okay, it'll be V times T, so 107.25 times 18.35. And again, in my calculator, I am keeping all of these decimals, right? I'm not gonna lose any of them. Okay, because of my significant digits, I gotta keep them all. All right, so it's gonna travel. What do we have? We have 2 significant digits, so it's going to travel 2.0 times 10 to the 3 meters, 2 kilometers. Okay, everybody all right with that? Okay, the other thing it wanted me to calculate was the maximum height. Okay, so the vertical displacement right here, where VF equals 0. Okay, now I can calculate my vertical displacement using VF squared minus VI squared over 2A. Then I don't have to forget and look silly for not using the correct time. Okay, so 0 squared minus 89.99 squared divided by 2 times negative 9.81. All right, so 0 minus that number squared divided by negative 19.62, which is 2 times 9.81. All right, it's going to reach a maximum height of 4.1 times 10 to the 2 meters. Above the ground. Okay? Everybody all right with that? All right then. All right, let's watch this. All right, so this one works a little bit differently. In this one, they don't give you the angle. All right? They're telling you it's thrown into the air at a velocity of 35 meters per second, but they don't give you the angle it's thrown at. Okay? So you know the magnitude, but not the direction of the hypotenuse of that triangle. Okay? It's in the air for 2 seconds and lands 70 meters horizontally from the point it was thrown. equal height. Okay? At what angle was it thrown? So in this one, you are looking for the angle of launch. Okay? And you have the velocity of launch without the direction, okay? And you know some horizontal information. So you can work backwards a little bit on this one. Okay? All right, so here's what we know. We know this is 35 meters per second. We don't know the angle, it's what we're trying to find. We do know that it's going to do this, because all projectiles do that. Okay? Horizontally, we know that its horizontal displacement is 70 meters, and we know that it takes 2.5 seconds. Now, they gave us time. Is that big? Yeah, because I can use it in both the vertical and the horizontal part. Okay, so that's helpful. Okay, so that's the stuff I know right now. Can I calculate anything right now? Right, I can calculate the horizontal velocity. Okay, so I'm going to calculate that by just going d over t. Okay, so that'll be 70 divided by 2.5.
How does that be 20?
Okay, so now I've got my horizontal velocity. I've got this side of the triangle. Can I get the angle now? Yeah. Is that like, does it seem harder when you first read it, but way less work than the other ones? Yeah. Okay. All right, so on this one here then, if I want to get theta, I have the adjacent side and I have the hypotenuse, so that'll be cos to the -1 of 28 over 35. Okay, and that'll give me theta. So second cos, 28 divided by 35. So we're looking at an angle of 37 degrees above the horizontal. Okay, everybody all right with that one? Okay, so some of these questions, they seem like they're like a lot different, but in the end, we still needed a lot of the same stuff. Okay, I was able to calculate something with the horizontal information right off the bat that then I could then use to get this. Okay, so this one is looking for the velocity it was thrown at. So that means you're looking for this and this. This one is mathematically not difficult, but there's a trick to getting to the math. Okay, there's an understanding thing with the vertical information that you'll need to figure out before you can get it. Okay, so this is fired from here, landing here, same height. Okay, landing and beginning are the same height. Give you some time on that one, because this one, it's an intellectual challenge. Once you pass the intellectual challenge, the math is easy. Okay. All right, so right off the bat, we can calculate V horizontal, because we're told it goes 30 meters in 10 seconds, so we just go d over t, 30 over 10 is 3.0 meters per second. So I know this side. Okay, but if I want to find the hypotenuse and the angle, I need at least one more side. And practically speaking, the only one I have any hope of getting is that one. But I don't have a lot of vertical information. But I have this. If something goes up in the air and comes back down to the same height, how do VI and VF compare? They're the same, but one is negative. All right, so if I'm looking at this formula here, okay, I have this number, I have the time is 10 seconds. And I have this, it's 9.81, negative 9.81. And these two numbers are the same number. Okay, one's negative. So if they're the same magnitude, do I need to have F and I here?
Not really.
No. I could just do this. This is the math trick. They're the same number. One's negative, one's positive. So rather than make them look like they're different, I'm going to make them like they're the same because they are. Okay? So now instead of having two unknown variables in this formula, I only have one unknown variable because negative v minus v is negative 2v. That's the math trick. Can I now solve for v? Yes. Okay. Now, what gets you there is understanding that VF and VI are equal in magnitude but opposite in direction. Since they're equal in magnitude, I can just make them the same variable but make one of them negative. Okay. That allows me to solve for them at the same time. Okay. So I can say that A times T over negative 2 should give me, well, V, but in this case VI, because that's what I'm looking for. All right, so if I take 98.1, because that's A times T, okay, and divide that by negative 2, sorry, that was supposed to be negative on the top too, I get 49.05. So, that's going to look weird. So when I do this now, this is going to be strange because my diagram is totally not right because this side is 49.05 and this side is 3. So this thing was fired like almost vertically into the air. Okay, and that's fine. That's just the way the question sets up. Okay, so now I can calculate the hypotenuse. So I'm going to take my 49.05 squared plus 3 squared. And square root that. Alright, so my projected velocity is 49.1 meters per second. I only have 2 sig digs, so it's going to be 49. Okay, and then the angle, since I have the opposite and adjacent sides, is going to be opposite divided by adjacent. And it's fired at 87 degrees, which is almost straight up in the air. Okay. What's that?
Only if it was 90.
Only if it was 9. It's almost straight up in the air, so it'll land like 2 feet away. Okay. All right, everyone okay with that one? It's just a math trick. I would never put one like that on a unit exam, just so you're aware. Okay, I'm gonna put one on there like I told you before, like this morning. Okay, so now this one's a little bit different. Okay, so we have a ball that rolls off an incline that is inclined 30 degrees above the horizontal at a velocity of 12 meters per second. Okay, and it lands 1.4 meters from the base of the incline. How far above the ground is the incline? So now this is the one you were talking about, bro. All right, so the situation I have here is I have an incline on a table, like so. Okay, the object's going to go off of that at 12.0 meters per second, 30 degrees above the horizontal, and it's going to do this. And it's going to land 1.4 meters from the base of the incline. Okay, we're looking for how far above the floor the incline is. Okay? So to here. This would then, what would we call this? This would be the what? If I'm talking about my vertical information, I would have things like VI, A, T, D. Yeah. This is my vertical displacement. That's what I'm looking for. Let's see what we can find here. Do I still have the projected velocity and the angle here? Can I still calculate the two things I always calculate with those?
Yes.
Yeah, I can calculate V horizontal and VI vertical. Right, so those should be your first moves. Right? Calculating VI vertical, okay, is going to be the sine of 30 times 12, which is 6.0 meters per second. Positive. Okay. V horizontal, that's going to be the cos of 30 times 12. All right, 10.39. Okay, what can I calculate now? Time. Yeah, I have enough information now with my horizontal data to get the time, which is something I can use over in the vertical data. And it'll probably be helpful because I'm looking for D, and I would have VI, A, and T at that point. I'll give you a minute to catch up. Okay, so if we want to find the time, we take the horizontal distance, 1.4, and we divide by the horizontal velocity. So this is a very short time, 0.13 seconds. Okay, but it doesn't go very far. It's going really fast horizontally, okay, but it's obviously not going very fast vertically, or it's not very high. Like this is some little kid's ramp that's, you know, this high off the ground. It's fine. That's just the way it worked out. Okay? If you ever like had little, you know, like dinky cars as a kid, and you're like throwing them off the ramps, that this is kind of like what that is. They're not in the air for very long. Okay. So we got 0.134 as our time. That can come over here. Okay. And now we can calculate D. VI times T plus 1/2 AT squared. Okay. So we'll have our 6 times 0.134. Plus 1/2 times negative 9.81 times 0.134 squared. Okay, so 6 times that number plus 0.5 times negative 9.81 times that number squared. All right, so it's 0.72 meters above the ground. So it doesn't take long, right? So it was only this high off the ground. And it wouldn't take long for it to reach the ground after that. All right. Questions on that one? So are there lots of ways and like lots of variations, permutations and combinations of what I can give you in a projectile question? Yes, there are.